Okay, my friends, it's going to be a lot of fun, especially for me. I've been saying that light has the white part of light has no weight, and that's true. This guy charged up his car, and it weighed before he charged it up, it was 3,492 pounds. This is a vehicle scale, and it's very nicely done, and I show this in a little more detail a little later. But after it was charged, this is after the charge, 3,492 pounds. Now, he can go another couple hundred miles. There's no weight. What happened? Where does it get the energy to do that if there's no weight being used? And I think I can understand, and I can make you understand what energy is, and it is nothing but this white part. It's nothing but the white part, which is this red, white, blue, green, it doesn't matter. That's the black part. And that there is the mass. And you're going to see all this very shortly. Physics has to change. Not complete, but quite a bit of it. And I'm going to show you that. And again, the only thing that exists is these two particles. That's it. Those are the tiniest particles there are, and that's all that exists. Everything else is made of those. And again, I will get into all of this very deeply in a minute. And I'm probably going to challenge you to try to figure something out, which has got me a little kind of confused. Now, this is where light has to pass through coming to us, so it's slowing down in space. The redshift, planetary expansion, all this Einstein nonsense. They're talking about Einstein's big, where is it? Somewhere around here. Yeah, right here. Einstein's puzzle unraveling the mystery of why the universe is accelerating faster. It's expanding, and now it's accelerating faster. That's just nonsense. Light is just slowing down more and more and more. That's all. Because they think light is being stretched as it gets pulled away. It's not that way at all. Light is just getting stretched because it's slowing down. Okay, before we get started, I want to make you understand that the dipole electron flood theory, it changes literally everything, because all that exists is the black and the glowy particle. All right, so, and they come red, blue, green, all different colors. Now, other than that, the actual look of the atom is going to be pretty close, because the proton, the center of the proton, is the dark matter. And it's like a positive. Let's call it a positive, because that's what they would call it. And it does collect together in a ball by itself, I believe. And it gets crusted by the electrons, which are the white particles. All right? So there's going to be a certain number of central particles, and then they will have a certain number that will be just right to fit into those little cavities. Each little cavity will have an electron attached to it. Somebody with a computer model could figure this out, how big they would have to be and what the energy levels would be and so forth. Because you'd have a ball like this of black particles, and every black particle is exactly the same size. So let's say there was 1,800, or let's say there was 1,000 of them, and they went into a ball configuration. You're going to have little cups of magnetic signature here and here and here and here and here and here and here, all over. There's going to be a bazillion of them coating this surface. It should be quite I don't know. You'd have to figure out something on a computer, how many particles there would be. Now, if this got bigger and a certain size, you'd end up with layers of electrons above this, which is what they have, the quantum. So I'm going with the look of the atom staying the same. However, the particles are totally different, because there is no quarks and all these other things they claim. All they are is made of these two particles. And the black and the red, or the black and whatever together, is an electron. All right? Then you go two of those together, makes a photon. And again, I've shown this many, many times. All right, so don't forget, this is my model now, and the closest particles that are to the core are going to be held so tightly that when they take off, they're the real brilliant colors, the blues and the greens and stuff, and way out at the edge is the red. Now, is there dark particles in between these layers? I don't think so. I think they all go to the center, and then you cluster around that with the white particles. And they did this in space, the Russians. And this goes way back, 2014, 2015. And I communicated to them that I understood, and I sent some information to them. And I didn't hear back, but I did send them, and I said, I think I understand what you got going here. These particles can exist in this white crust, because they freaked out. So during the experiment, we contacted the Earth guys who couldn't believe it either. They had a vacuum chamber, which means there's nothing whatsoever in there. And then they injected these charged particles in there, which means they have extra electrons. And they just closed this, pushed all the black matter to the center and coated it with the white matter, which is basically what electron flood theory would predict would happen, because it's the center becomes the black and crusted over with the white. Now out in space, you saw it was a little bit flat. That's because of gravity. Down on Earth, you'd never see this because it lays flat. It can't surround itself in big balls, and that's why they say there's dark matter forming. There's a dark hole, black hole forming out there. Well, yes, it will get bigger and bigger and bigger. Yes, dark matter can collect into a ball. I don't disagree with that whatsoever. All right, now I'm sure I'm going to go deep into all of this stuff in a minute, but I just want to clear up the issues. These are the ones that they found at Fermilab and CERN, which is the black ball with the glowy edge around, and that never changes size, ever, never. That's why they can collect in the center of things, and there'll be a known quantity that would surround it. It's not like they're fluffy and mushy. They're always the same size, like little bowling balls, and they're always the same size bowling ball. These are just gushy and floppy, and they are where all the energy is. And we did this with light, not with the huge particles like they use, because they see a debris. We see the actual light itself manifesting itself. This is as it's traveling through the air. That's a photon. And this is what it looks like. And here's the black with the glowy edge, exactly like they say at CERN and Fermilab. And these ones get glowy and puff up because they're hitting these particles in front. You see those little particles? All right, those particles are interacting, they're fields. Anytime a field interacts with a field, it pushes it and shoves it, and they glow. And that's what's happening as this is trying to accelerate through these fields. All right, because that's in the acceleration phase. Anyway, like I say, I'm going to be showing you that Einstein was not correct. And these are the particles, smallest particles they can find, and they do exactly what they claim. That one there is a bowling ball, never changes size. That's a gushy little bugger. And that one can squirt through, which it does. And we separated these two, which is fission, right here. And then they came back together, which is fusion. This is electron showers, which is precisely what they want to see. And we can do this on a continuous basis, shooting light through here. Not big photons, protons. Protons are just too big. They're huge. They're big things like this. We're coming through there with this. Right through. And so we're not damaging it. Because of the size of these, that's what causes the damage. In these big particle colliders, they smash these things together, and the big jobbers go flying everywhere. Well, we're hitting just light. That's all that is light. That's a photon of light coming out of a red pulsed laser. That's all it is. So we have a lot of thinking to do on how light works and how it reacts and how it spins and how the energy levels and the frequencies. And light can slow down in a vacuum of space, which is not a vacuum. And they know it's not. The same people who put this out, Fermilab, says it's a quantum foam. It's just saturated with subatomic particles, which is true. Light is a subatomic particle. And light comes, as you see it, from the sun to us. It doesn't just come here from nowhere. So it's filled, the universe is completely saturated with these particles. And as I showed you, these little particles, they interact. They interact. They interact. act. What does that tell you? It tells me that it's going to slow down that light. It's going to slow it down as it pushes against it. It's no other alternative. And I can show you the light slowing down. In this case, it's speeding up, smashing into these particles, making them glow. In other cases, it's just slowing down because its normal speed is being diminished. That's what they call a red shift. So it's not that the galaxies are all pulling away from each other, everything's expanding. It's that the light coming to us is slowing down. So instead of being this speed, blue, which let's say blue is like this, and it spins. All right, so it's spinning and it's this close together. If you look at it, that's a wave. But it's not flapping, it's spinning. Now, once it starts banging, it goes boom, 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 boom. Ever see the fields? They show fields with all the lines. That's where it's coming through. It's coming through real hot and bang, 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 bang. And then they just spread out and they shift to the red. By the time they hit the Earth, they say, oh, look, it must have started out, I mean, the planet is being pulled away. And the planet is just being pulled away, so the light we see is now red instead of blue. It's just not that way. The light we see is just slowing down. And again, I will show you light slowing down. And you can see light speeding up. All right, you can see that. I mean, it's quite obvious. And here, it just divides itself. That's right here. It divides from the white into the black, which is muons, which are the black particles. They never change, and that's what's called a sterile muon, from a muon neutrino. An electron neutrino turns into an electron shower. That's it. And that is exactly the stuff you want to put into your battery. We separated it here. That's the whole key of a generator, is to separate the white from the black. That's all a generator does. All you want in your battery is this white stuff. The black stuff is you got to keep out. That's what we just did. We separated the black from the white. We should be able to take that white and just let it push it right down right here through a receiver down into a battery, right through a photodiode. And then it's there. It goes through the gate and it can't get back out. And these are just slapping it. Boom, 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 pulse. And you could change the pulse, you could change the venturi, you could do all kinds of stuff. And then you have to have a receiver back here that absorbs these frequencies. And that is also fully understood now. They're using all kinds of new transition metal little things and so forth to absorb different energy levels as actually these white particles, these electron neutrinos. And then they just push them down into your battery. Now, when you go driving around in a car that has batteries, a Tesla, let's say, you usually get driving around all over the place, up hills, down hills, around the corners, 500 miles, you come back, you charge it up. Well, when you came back, your car weighed 5,000 pounds. All right? It doesn't, there's no energy in it at all. It's just, and it stops. You charge it up. It weighed 5,000 pounds. You charge it up. How much does it weigh now? Right? Think about it. You charge your battery up in your car, and it's good for another 500 miles. How much does it weigh, whatever you put into that battery? How much does your car weigh now? If it weighed 5,000 before, what does it weigh now? Fully charged and ready to go again. Okay, this is from atomcentral.com, and they are going to show an atomic bomb blast. Now, they have a camera facing away from the blast so it doesn't destroy the camera, and it's in a hardened enclosure, so they're watching what's going to happen. Now, I'm going to tell you what is going to happen. When an atomic bomb blast goes off, the black particles push the white. The white is always encrusting them. The white is everywhere. So the white goes out first, and then the black follows it. The white has no mass. Remember this. Very important to remember this. The white has no mass. It's not going to push anything. It's not going to knock the house over, but it's going to burn the house up. And it is the first thing that comes because it's always on the outside. So boom, it goes off. out comes the white. And it just smokes everything up. It burns it because it has no weight to it. And as I showed you, or will show you, when they weighed that car, after it being depleted with energy and then filled back up again, it gained no weight to speak of. It did gain a tiny bit of weight. They say no, it didn't gain anything. But I know for a fact it had to gain something because we put electrons into there. They weigh almost nothing, and really almost nothing. But in the weights and measures, they force you to calibrate your weights only when they weigh the same, when they are at the same temperature. And temperature is nothing more than extra electrons. As far in my mind, that's because they say a hot item will weigh a little bit more than a cold item. And that's all it is. It's taking on some electrons. You always think of something getting hot, it floats up in the air. No, that's only gases that expand. If you put heat into something that's solid, it's going to be a tiny, tiny little bit heavier. And I know this very, very certainly for no question whatsoever because I had to get weights certified at the Weights and Measures. And they told me, you have to leave them over here for 24 hours. They have to be the same temperature as the room. Otherwise, they can't certify them. So we're going to see that white coming out here that has no weight. And we're going to see it all burn up. And then the black is going to hit it and knock the house over. And I've got it running slow motion, quite slow. So here it goes. Now I got to turn off the sound. All right, so here it comes. The first thing you see, that's just a glow. Everything glows, all of the particles in the air. And now everything's just smoking up. Nothing moved. I'm going to stop it right here. Look at the wires, the poles. Everything that's combustible is burning up. The metal is not going to burn up. And it's being hit just like all this. The side is not being hit, but the front is being hit and just smoking up. Now, as we go forward, eventually all that just will be basically gone, and then the black comes and smashes it down. All right, so you ready? Here it comes. I'm going to just finish up here. Now, it just keeps smoking up, smoking up, smoking up, smoking up, smoking up. Boom! Then that black hits. So we have two obviously separate events of one that has no mass and one that has all the mass. The white has no mass, the black has all the mass. Okay, get ready, my friends. This is the solution to my question. This is only 2 minutes and 48 seconds long. You can come up and watch the whole thing if you want, but this is John, and this is the evolving world, and he's saying, does a fully charged battery weigh more than when it's empty? And I say, I thought there was going to be a difference, but it appears there isn't a difference, and now I think I understand why, and I thank John for his work here. All right, so this is what John did. He took 4 of these weight sensors, and he tied them all together and weighed the car prior to and after being charged. Okay, so here's what John's doing. He's weighing this, and he's got all 4 sensors tied together, and he's going to see how many pounds there is. All right, 3492. That's all 4 of these. Each one of these is, and then it figures out the percentage per weighing, but it's virtually 3492 is the weight. You see it? 3492, 3491, 3492. All right, that's the number of pounds. Now, let's see what happens after he charges it, because it's not charged up now. All right, here he is. This is John, and he's weighing his car as the battery's depleted. 3,492 pounds. Now, he goes through all the steps, and he shows how he's charging it up, and he's plugging it in and charging it up and all that stuff. And now he gets to the point where he's coming around and he says, okay, any bets? Who's going to bet how much you get? Remember, it was 3,492 pounds. Now, this is after charging.
Here, so what do you think it is? 10 pounds? 5 pounds? No pounds? Well, here it is.
No pounds.
That's kind of interesting. Not totally surprised, but then again, there's a part of me that is a little bit puzzled by that.
It didn't gain any weight at all. It didn't gain no weight whatsoever. So he can drive another, I don't know, let's say a couple hundred miles, and then charged up again, it's never gained or lost any weight. How could you, where did the energy come from? All right, so don't forget now, this is a vehicle scale with all 4 wheels on it, and it didn't gain any weight at all. It didn't gain any weight at all. All right, it was, it maybe even lost a pound. I didn't lose a pound, but it's 34.92 watts. See, it's 34.91, 34.92.
So basically, 0 pound difference here.
All right, so there was no gain in weight. Let's put it that way. And you can go, let's say 200 miles, it would be about 60 pounds of gasoline to go 200 miles. Where did the energy come from? What actually happened to create the energy, make those wheels turn? We didn't use anything up. All right, let me just explain mirrors to you. Very simple. They use a metal reflective surface, and what that means is all the light that hits it can't be absorbed. It bounces back. And there's different metals give better or less quality light, but silver works very well. Now, when light hits a mirror, it bounces back all of the different colors, all of them, because all of this stuff that's hitting is bouncing back. Now, why don't we see, we can see different colors here. Well, how does that work? It's all the same light that's hitting it. Well, the key is that the ink that made this stuff is made out of different types of molecules, and they will only reflect back a certain frequency. And that's how transition metals work. And here they are right here. These are transition metals. Now, I don't know whether they use metals in these colors. I really don't know that much about the dyes and all that business, but I know that they're only reflecting back a certain frequency of light, which corresponds to its color. And that's what the spectrum is. The more and more frequency you have, the more and more you head towards the blue, which means the faster the spin of the particles, which means the more impact. Blue is a real serious impact. Green is a little less. Red is the lightest amount of impact in the visible spectrum. Okay, so as you recall, when they charged up the car, it still stayed 34.92. There was no difference. All right? Now, I would have expected there to be some difference because of my experience with the weights and measures people, knowing that weights had to be the same temperature. And I always corresponded temperature to being electrons, extra electrons, which are the heat portion. But you would actually have both of these particles together, and that is what heat is. It's just because you still have the white one. The white one is heat. I don't care whether it's attached to this or not. The white one is heat, and the black one is attached to it. Here on Earth, they can't separate easily. The only way they can separate is to do what we did, was put them through this Venturi. All right, and then we can separate the black from the white. Remember, these are the 2 particles they want to see from Fermilab, and they're the 2 here. Now, the key here is that they're attached together. They see them apart, and they don't realize, I don't think, that they are normally attached together. And 2 of them back to back, which makes a photon, is light, and it's pretty stable. And it hits and it bounces because it's got a big field surrounding it. Just one of these is what they call a gluon, or in my case, I call it an electron. And that is what flows through the wires and everything, with the black with it, apparently. Or it's just heat, one or the other. This is still a little bit up in the air. Heat could be just a black and a white together. Electricity, though, could be just strictly the white, just the white, trying to get back to the black. And I think that's the case. So we have 2 situations. We have the black and the white together is heat, and that has a weight to it. The white all by itself is electricity. It has no weight. And what we did was we separated that white from the black. And that's exactly what you want to do to put it in your battery. Because this white will go into that battery and it won't charge it up. It'll charge it up, but it won't increase its weight. And that's exactly what happened when the guy charged his batteries. John charged his battery up and it didn't increase any weight whatsoever. And he's got another couple hundred miles he can drive now. White weighs nothing. I am kind of, I got to be honest with you, I'm shocked. I expected there would be some increase in weight, but it appears that they're right. Fermilab appears that they're right, that this has no weight whatsoever, and this has all the weight and has all the mass. So I'm going to have to go with that. And I'm telling you right now, I have come a little closer to the standard model. They don't understand the bits and pieces in the standard model. They still think there's big chunks. But I'm getting a little closer to their interpretation of standard model with one big solid positive core and surrounded by a bunch of little electrons, which weigh virtually nothing. And the core just gets bigger and bigger and bigger as you get further and further up the periodic table. So hydrogen is down here, but it consists of 1,823 of these two attached together, except when they get attached together like that, it pushes the black right into the center, surrounds it with the white. All right, so their model is wrong because the proton in the center, the nucleus in the center, is not one gigantic thing and just one little electron. No, it's the same number of black particles and the same number of white particles surrounding it. So it's quite a bit different, the standard model, than my model. But I would agree there's going to be one big solid chunk in the center and then surrounded by electrons, but a lot more electrons than they're talking about. A lot more. Because there's 1,823 of these black particles in a proton. So there's going to be 1,823 of these white ones, not one. Right now they say hydrogen is one big black one and one tiny little white one. It says, but the same charge. No, it's 1,823 of the black ones in a ball, and then 1,823 of the white ones crusting around it. All right. When you get up into into these numbers here, you get a solid black core, and then you get a ton of electrons surrounding it, and I mean a ton. That accounts for the isotopes. That's why these numbers are very meaningless at this point. Chemistry has to change. Everything has to change. That's why I say we all need all new books. Everything's got to start over again, and I mean really everything. Okay, here's what's wrong about the standard model. First of all, let me show you what's right about it. There's a white particle and a black particle, and those two together add together, yes, to make what they call a gluon, which is the two white and the black, and two gluons make a photon. That's the only thing there is. Higgs does not decay into a W and a Z boson. Higgs becomes a Higgs when the two come back together. All right, and they don't realize they have this backwards. All of this stuff is nothing more than these in different states of excitation, neutrinos spinning up, spinning down, all that business. So this is the only thing that matters in a standard model, and really the only two particles that do exist is this and this. And the two of them together make a Higgs, and these two together, the Higgs, when they see it, is when they recombine. All right, normally the Higgs is, you don't see a Higgs. The only time you see it is when these two slam together and then they make this big field. That's when you see the Higgs. It's not the other way around where the Higgs decays, and that's the way they claim. Totally wrong. Then these two make a gluon, two gluons make a photon. I don't recall if I showed you this or not about the Russians in space putting in charged particles into a vacuum chamber, and it created this void in the center crusted around with all the white particles. And that's exactly what I would expect. And I also expect the flatness of it. The reason is there is still gravitational influence to this. So it's coming down. On our Earth, this would just be a mix. You wouldn't see a black hole in here whatsoever. Black holes can form in space. They're right. They say, well, the black hole is getting bigger, getting bigger. And they will. They'll collect more and more blackness and get bigger and bigger and bigger, and the white will get more and more whiter around it, and it will become a very brilliant black hole. Black holes turn into really extremely brilliant things out in space, because the more black here, the more white is going to be drawn to it. And as they're scrubbing through space, this makes a lot of energy. Again, I don't think I showed you this yet either, but I'm not sure. I did get interrupted a number of times. This is just out today or yesterday. Einstein's puzzle unraveling the mystery of the universe's accelerating expansion. It's growing faster and faster, expanding. It is not. The light is just slowing down, coming through all the fields in space. And they still want to hold on to this theory that there is nothing in space. Space is saturated with fields. I have shown this, and we've actually seen it just using a cell phone. You can see it. They say the universe is expanding, accelerating rate, possibly driven by dark energy. No, it's not. However, the Hubble tension is a discrepancy in expansion rate measurements, challenges current models, and spurs ongoing research for explanations. Well, I have the explanation, my friend. It is slowing down. It's not anything's expanding. Well, okay, my friends, this turned me on because I'm doing all this stuff about the light research and how the photons bounce and all this stuff. And I'm thinking, well, I'll show a Crookes radiometer. I'll be able to explain this really easy. So I come up here and this is applied science. Now, he's showing a Crookes radiometer. The way this works is there's a black side and a white side on each one of these vanes. And when you shine light on it, it makes the black side push around in a circle like this. Now, then he puts cold on here, and it makes it go backwards. All right, cold, there's a difference between cold and light. Light is heat, and cold is the lack of heat or the suction of heat away from something. Now, he's coming up with some kind of a conclusion, and this is stimulating me, and his conclusion is not right, I don't think. But let's let Ben talk here. And this is a Crookes radiometer. Now, something else you have to remember is inside this glass chamber, there's nothing, it's a vacuum. So there's nothing for it to push against, or there's nothing for it to bounce into. That's two different things. So now don't forget, applied science, and this is Ben, and here he goes. He's going to talk about this. Here goes.
Is actually much higher that causes it to spin. So there must be some other explanation for its movement. So let's try something else. I've let the radiometer come to rest by...
Before I go any further, the reason he's saying there must be some other reason, he's saying that the white is the one that should be pushing that way, it should be spinning, because the white will make it bounce back. I'm not sure he understands light, which nobody really does. It's both black and white. So here you go, let's go. Because they can just consider it a white particle, but it's not. It has a massive particle and it has a bright particle. Here it goes.
Itself. And I'm going to spray some of this on it. This is a canned air duster, which is actually a refrigerant. And what I'm going to do is tip it upside down and spray some of the refrigerant on the glass envelope of the radiometer.
It goes back the other way.
And as you can see, it's actually spinning backwards relative to the way that it was spinning when we shined the light bulb on it. So clearly there is something else going on here. If it were just a photon effect, making the glass envelope cold would not cause it to spin backwards, because we aren't.
All right, he's saying if it was just a photon effect. Well, a photon and an electron and a dipole electron, they're all exactly the same thing. It's just that a dipole electron is only one, and two of them back to back make a photon. And then in big chunks, they tend up being protons and so forth and going up the chain. So what has actually happened to draw this thing to spin the other direction just because it got cold? Well, what would the cold do to a vacuum? Because there's a vacuum in here. What would the cold do to a vacuum? What would the heat do to a vacuum? I'm gonna tell you what. Let's just sit back and think about this, because I'm going to sit back and think about it, because I really didn't give it that much consideration. I thought I'd come up here and just be able to explain it very easily. The light bounces off, and they didn't realize that black absorbs and blah, blah, blah. So, but that's not the case. It's a little more complicated than I thought. So let's stop and think about this. I might continue on here after I get a few minutes to think. But I might also just let you have it and figure it out yourself and try to figure why does it spin this way with the light and that way with the cold? Why? There's obviously a reason. And don't forget, it's a vacuum. Something's going on here. All right, my friends. Normally, I like to be the one that says, oh, this is how this works, this is how this works. Well, I don't know exactly how this does work. But this is a Crookes radiometer. I know how it appears to work. But what is the actual mechanism? What is making that vane spin around in a circle? And it's related to heat and cold and pressure. And pressure means how much gas is in this almost complete vacuum, but it's not a complete vacuum. There has to be a certain amount of gases in here, and that's pressure. Now, this is applied science. The guy's name is Ben. Very, very good guy. How a Crookes radiometer works. So you can come up and watch that if you want, and that's where it is. You have to search for it. Now, Applied Science is the guy, and it's just fabulous. And he's got all the toys, trust me. And he's got this big vacuum chamber here, and he's going to put it in here and see how much pressure, and then he's going to see how it spins. He's got all kinds of things going on. Oscilloscopes all tied in, and But I don't think we need all this stuff to understand the principles behind this, because electron flood theory covers this. They still really don't have any idea. They talk about thermal transpiration and this and that and so forth. But his first assumption, I'm going to tell you right now, I don't agree with. Hold on one second. All right, let me just explain what he's going to say. He's going to say that because you're shining the light on it, hitting the white should make it spin like this direction. But it doesn't. It spins in the other direction, hitting the black. Now listen to what he has to say.
The radiometer starts to spin, and the brighter the light, the quicker it spins. But what actually makes it spin? You might be tempted to think that it has something to do with the photons themselves. So the photons that are emitted by the light bulb hit the radiometer, and it's actually the momentum of the photons that cause it to spin. However, look more closely. As you can see, it's actually the black face that's trailing, meaning that there's more force on the black face than there is on the white face of the radiometer vanes. Now, if we think about the photons coming out of here, they would actually be reflected off the white sides and absorbed on the black sides. So that would mean that they're actually delivering more force to the white faces, and it would cause it to spin the other way. So,
all right, so that's his conclusion, that it's spinning, something else is going on. Let me just let him finish up.
The explanation that light pressure causes this radiometer to spin is actually completely wrong. It would spin the other way if it were true.
All right, so that's he's got it completely wrong. Well, I'm not saying he's completely wrong. I'm saying he's saying this is completely wrong if you think it's the light pressure. Well, what do we know about this? We know there's a glass envelope here, and then we know there's some kind of tiny little bit of gases in here. You have to have a certain amount of gas, it won't spin. And what do we know about glass? What do we know about everything? Is that on the surface of every single thing, on the surface, so the outside surface and the inside surface, is going to be electrons. Not the black particles. The black particles are inside the electrons. The electrons are always coat every single thing. All right, so we've got electrons on the outside, electrons on the inside, and then we've got gases, and then we hit these things. Well, the light is obviously sending some kind of energy into this mix here and making the black spin around this way. What is the interaction between the gases, the outside electrons, the inside electrons, the gases, and then making the black be pushed to spin? Because it is something to do with the light, quite obviously. It's the photons of light that are creating some kind of a force that's pushing this, but not the white. And this is where it gets pretty tricky. I'm going to tell you right now, I'm a little confused with this. So I'm not going to probably say what I feel is the cause of this today. I'm going to let you think about this so you come up with your own conclusion. And then probably at the next time I do a video or next few days, this will eat away at me. I won't be able to sleep until I can figure this out. But I can tell you one thing. It's got something to do with these layers of electrons, then the glass, then the electrons, and then into this very, very lightly, a very light amount of gases in here. Somehow it's transferring that energy, and it's energy, and it's pushing. And I know from the atomic bomb blast, the black will push the white. And now we're seeing, can the white push the black? And it appears the white can push the black under the right circumstances. All right, we know the black can push the white. That's no question. We've seen that in the atomic bomb blast, or you will see it. And I can show you that in our light experiments. Absolutely zero question, the black pushes the white. Can the white push the black? All right, so don't forget, when the light hits it, it pushes the black and it spins around this way. When you put cold on here, it makes it go the opposite direction. So cold makes it turn wrong this way, hot makes it turn this way. And the same thing, you don't need the light on here. If you put your hands on there and warm it up, it'll spin just like with the light. So it's a thermal situation. Cold makes it go that way, hot makes it go this way. All right, so light is just a mechanism to deliver some small amount of heat. All right, so this is what's got me a little on edge here. There's a lot of things going on you don't realize. You just see the light shining on this and the thing spins. And most people just say, oh yeah, the light is pushing that. Well, they say, no, that's not true because it's hitting the black and the white should be spinning. And then they go on a lot of stories about this, but they still don't understand it. Nobody does. Nobody understands how a Crookes radiometer works. It's thermal, they know that. If you put cold on there, it'll go the other direction. You put on here, it goes this direction. Why? Why? And the cold, he sprayed some stuff on here, and it made it go this direction. Because it was a cold stuff. And then when you heat it up, it goes the other direction. The black gets pushed around. Cold makes the white get pushed around. Why? And it's cold, it's not light. And you don't have to have a light here. You can just do this with your hands, with the temperature of your hands on that glass, it'll start spinning. So it's absolutely 100%, it's thermal. What is the thermal reason for this? They've got some kind of really exotic ideas of thermal transpiration of the edges and all kinds of things, but I don't buy any of that. Well, I don't know what I buy. I'm not ready to make a purchase. How about that? So I'm going to probably ask you to come up with your solution, and then in my next video or soon, I will tell you what I think. Because there's no question whatsoever. There's something going on with the thermal, and there's absolutely no question that it can be figured out. It may take a little bit of trickiness to do it, but I have a bunch of stuff here. As a matter of fact, hold on. I'm getting ready to start really investigating this. It's just what I do. All right. So first of all, you got to figure out what is light and versus heat versus cold versus electricity. And the photons and the gluons and extreme fire is resistance. Extreme heat it creates gigantic amounts of resistance to the flow of the energy, and you get a fire. Cold is just the opposite, and you get superconductivity because there's no more electrons in there. So what are we dealing with here exactly? All right, so I'm saying electricity is just the white, and you push that electricity into your battery. You didn't charge up, you didn't make your battery get heavier, you just made it get more powerful. Because the white has no energy, no weight. Electricity, which is what you want to put into your battery, is the white only. It creates strong attraction to the dark, and that's what makes it go drive your wheels in your car. Now, earth ground must be excessive dark energy because the white wants to get to earth ground. So there's got to be a lot of extra dark energy in the earth. Now, heat must be excess gluons, which are the black and white together, because heat adds weight. So the black has the weight. All right, and then I go on about the reflectivity of the black and the white and the bounce and so forth. And then these are the questions I have, and you should be asking your own self. What does a laser do with this radiometer? And I know about that a little bit now because I started looking into it. These are questions I ask myself, and then I go back and I try to answer. Now, if you point the laser at the white, what if you point it at the black? What about different colors? And what about the ambient light that's in the room? How does that affect things? Different colors and different temperatures. Most of this stuff I've already figured out. But this is stuff you should look into if you want to figure something out. This is how you do it. You got to start from the beginning. I say only blacks or whites or alternate. What if you just hit it? Anyway, what if you put in 3 black ones and 1 white one? What would happen? Would it spin? I think I've answered most of my questions about most of those things. Now, hot spins the thing in one direction, cold spins the thing in the other direction. Light is heat. That's no other way to put it. Light brings in heat, which is extra electrons and extra muons. Light is both of those things, electrons and muons. So it's got the weight of the muon and it's got the energy of the electron. That's what light is, and it is also heat. Now, cold is the lack of electrons, just the white part. Just the white part is gone. So the white part is they don't have any weight. Lack of electrons means you can draw all those little puppies out of there, and it doesn't change any weight. Cold doesn't make things get lighter or heavier, because the weight is what you're drawing out. So the muons do not change. I don't think the muons leave with the electrons. The electrons go, and the colder it gets, the more conductivity you have, because there's not enough electrons in there. It wants them to come in. And when you get down to superconductivity, absolute zero means there's absolutely zero electrons in there. It wants all you can give it. And then when you get superconductive, just for an instant, it starts to fill back up, and it creates resistance. You have to continuously keep that thing in that cold phase, which is more energy than you're ever going to get back. All right, superconductivity is not the key. Now, so the cold is the lack of electrons. The muons don't change. Therefore, the mass does not change. The mass of the thing doesn't change. It still weighs the same. Now, there's a vacuum inside here, not quite vacuum inside, and there's some extra particles in here, but just a few. And they're just normal gases, I guess. There's nothing special about those gases. So 100% of the matter is coated with electrons inside and out of the glass. That's what they're not taking into account, because everything there is, all matter, is coated with electrons. It's always electrons on the outside, or in this case on the inside as well. So there's an excess of electrons out here and an excess of electrons on the inside. And it's not a vacuum, right? And you must have some pressure. And here it is right here. A centimeter apart spins best. So the gas molecules are really far apart. A centimeter is huge compared to normally they're 100 nanometers. That's a billionth of a meter normal pressure. And I guess that's about it today. All right. So anyway, that's what we're going to get started with. And there's no question there's a reason for this. Absolutely no question whatsoever. It gets a little convoluted. I was surprised. I thought I was just going to come up here and say, okay, here it is. Have a nice day. Time to eat. No. Little harder than I thought. All right. This raises an extremely interesting question. This is the Venturi. This time, some black and some white is coming through. The white is highly accelerated, so we can see it very much glowing. But you can see the black is right behind it, pushing it. There's very little question, and as I'm going to show you shortly, an atomic bomb blast, the white comes and burns everything and doesn't even move the house whatsoever, doesn't even move it, it just burns up, and then the black comes and knocks it out. So this is all the mass, and this is all the burn. And we know from this picture, this one thing alone, we know that the black in itself can push the white, because the white is being pushed in front of the black. There's just no question about that. Can the white push the black? If we could we get the white on its own to push the black? And I don't think we can. We can create the white pushing into Higgs fields, which must contain the black, but it doesn't push like a wave of blackness like this is a wave of whiteness. Let me show you what happens when the white in concentration comes into a field just like this. This is just air. And what happens when the white comes in, it just creates all these Higgs fields. Okay, these are from light experiments Rod Warren and I did years ago, 8 years ago. And this is just light, pulsating red laser light, accelerating all the particles in front of it. It's just starting to accelerate. And it's as it pushes through all these other particles, their fields glow. And this field just obviously glows more because it's the big guy. Now, what happens when it does accelerate? Here's what happens right here. It pulls its particle, which is the particle, and it has a big field around it, so the field creates a wave. The particle is inside the field. Well, now the particle is pulled completely out of the wave. You see it? It's accelerating because of a venturi. And at that venturi, it explodes. And this is superluminescence. This is like on steroids luminescence. This should be enormous amounts of energy increase from what it was here. Now, so we've seen the particle just going by itself, and now it's accelerating. And now when this white shower comes out the other side, it doesn't create a wave like this. The black creates a wave of white, but the white creates a shower of this, of what they call Higgs bosons. See the white coming through? It's not creating a wave. It's creating these Higgs bosons. And the Higgs bosons are when the white reattaches to the black. They say it's the other way around. They say the black and the white are together and they decay, turning it into a white and a black little particle. It's just the opposite. The black and the white are separated and then they come back together, causes a Higgs field. As you can see, I mean, it's pretty apparent. So we have this one where the black pushes the white, and then we have here where the white all by itself just creates these fields. So it's just a different effect. And the Higgs fields are from CERN. This is from CERN. They say the same thing, only they're using gigantic particles, so they're seeing very similar patterns, but it's just a bunch of debris. Literally debris, because it's just smashed into bits of literally thousands and thousands of particles, where we have one particle that we're looking at. We're looking at the actual particle itself. And what can I say? As far as I'm concerned, we did exactly what they wanted to see, the black and the white particle, which is it right here. That's exactly it. And this one can glow and get big and small, which it is. The black one never changes size, but it has a glowy edge around it, exactly what they say. These are together, these are fused together. Well, fusion and fission are something that creates a lot of energy. These are just normally together, attached together. Well, if we could detach them, which we can, we broke the black away from the white. That's fission. Now, it automatically, instantaneously wants to be reattached to the black. That's what energy is all about. That's what, if you can separate the white, and we did. It's completely separate. Completely separate. Completely separated from the black. Not a single black particle is here. So what if we could harvest it right here? And I think I've shown that little device that I think we could harvest it right there and put it in a little box that we could carry around. It would be, I don't see any reason that this, because we know it doesn't weigh anything. The white weighs nothing. And if we got white here, if we can just make that go into a battery, we're golden. And all we did was shine it through a venturi. We didn't do anything extra. No generator, no, because that takes a lot of energy to generate electricity. It takes a lot of energy to force that white particle away from the other particles. This did it all by itself. All right, so think about these things now. This has got me thinking. There has to be some tiny amount of gases in here, but very sparse amount of gas. But something has to be in here. You've got glass separating this from out here. All right. When you warm this up, the black pushes around in this direction. When you make this cold, it goes just the opposite direction. Why? We don't need light. We don't need light. We just need heat, or we need cold. Heat makes it go one way, cold makes it go the other. This is your mission. Why? I'm going to leave it at that for today. I love you all. I'm going to be working on this because I know it's not what they think it is. They're talking about thermal transpiration of the edges of the corners or something. I don't know, but it's not that. And I think I already have it sort of figured out. But I really need to lay it out and draw diagrams and so forth so you can see precisely what is happening. The interaction between the dark and the light particles, because there is an interaction there. They push and they shove each other, and they attract to each other. So using all those understandings, we should be able to figure out how this works. All right? I love you all. We'll talk later. Thank you. Bye.